Okay, in this last video for 7.8, we're going to use the comparison theorem to determine whether improper integrals type 1 converge or diverge. Before we do that, there's an important fact that we're going to use on most of these problems, not all but most of them, and that is that the improper integral type 1 from 1 to infinity of x to the p, where p is a constant, it's going to converge if p is greater than 1. Not only does it converge, it converges to 1 over p minus 1. And otherwise it's going to diverge. That's a very important result. And it comes up next quarter in Math 153 as well. Okay, so for example, if you wanted to look at the improper integral from 1 to infinity of dx over x cubed, that's p equal 3. So therefore the integral converges. In fact, I'll tell you what it converges to. It converges to 1 over p minus 1, or 1/2. Let's say you had the integral from 5 to infinity of dx over x cubed. It would still converge. It wouldn't converge to 1/2. If you wanted to figure out what it converges to, 5 to infinity, you could take the whole integral from 1 to infinity, right? And then you could compute the integral from 1 to 5 of dx over x cubed and subtract that from this. That would tell you the integral from 5 to infinity, wouldn't it? Anyway, how about this one? This one, this is going to diverge because p is 1/3. Anyway, so here's what the comparison theorem says. It says, let's suppose two functions are greater than or equal to 0 as long as x is greater than a. It looks kind of like this. If the top function is f of x, and if the improper integral from a to infinity of f of x converges, since g of x is below f of x, there's less area under g of x than f of x. So if the area under f of x is finite, the area under g of x has to be finite. Conversely, if the improper integral from a to infinity of g of x diverges, which means this area is infinite, since there's more area under f of x, that area has to be infinite as well. So it makes sense. The trick with these problems is trying to figure out what to compare the integrand to. Let me give you some advice here. Ignore like the 3 and the 5. This is basically behaving like 1 over x squared. So I'm going to try to make this less than like something like 1 over x squared, or some constant times 1 over x squared. So the reasoning is kind of tricky. This one isn't too bad. I'm trying to make this less than something over x squared. Well, this one, all you have to do is realize that 3 over x squared plus 5 is actually less than 3 over x squared, because the denominator here is bigger, right? So this is actually, since the denominator is bigger, this whole thing is less than this one. We're not done though. We did the hard part. You also have to state that the integral from 2 to infinity of 3 over x squared converges with p equal 2. Therefore, by the comparison theorem, so does the integral from 2 to infinity of 3 over x squared plus 5 dx. Whatever you do, don't say that 3 over x squared converges. That's not that's not correct. It's the integral that converges, right? It's the integral from 2 to infinity of 3 over x squared dx that converges. All right, how about this one? Again, my advice in trying to figure out what to compare it to, forget about the 5 and just look at the highest power of x here. You basically have 1 over the square root of x squared that's behaving like x. So this whole thing is going to behave more or less like 1 over x. So I'm going to make this, since the integral, the improper integral diverges of 1 over x, I'm trying to make this integrand greater than 1 over x, okay? Or something over x. Okay, here's how you can reason that. Isn't it true that for x greater than 2, x squared minus x is less than x squared, right? Because you're subtracting stuff here. So if that's true, then if you square both, the left side will still be less than the right side. Now here's the tricky part. When you take the reciprocal, then, if this is less than this, and they're both positive, when you take the reciprocal, 1 over this is greater than 1 over this, which is just 1 over x. I'm not quite done, but I've done all the hard part. I've got that 1 over the square root of x squared minus x is greater than 1 over x. If you multiply both sides by 5, then they're still true. So there it is. I just showed that the integrand is greater than 5 over x. Furthermore, the improper integral from 2 to infinity of 5 over x diverges with p equal 1. So by the comparison theorem, the improper integral from 2 to infinity of 5 over square root of x squared minus x dx also diverges. Okay, that was pretty sneaky. This one isn't quite so bad. Here's some more advice. Whenever you see a sine or a cosine or a sine squared, recall that can never be any bigger than 1. So this really doesn't affect anything. So think of this integrand as basically t over t over t cubed, which means 1 over t squared. That's what this is behaving like. So what does that say? I'm going to try to make this integrand less than something over t squared. Okay, this is how we're going to do it. Remember, so I'm going to make this. I'm going to try to show that this converges. Well, sine squared t is less than a lot of things. It's less than 1, but it's also less than t, as long as t is greater than or equal to 1, right? So I can replace this with a bigger thing on the numerator, so therefore this integrand is going to be less than this thing. You see what I did? I'm noticing that this is obvious that sine squared t is less than or equal to t as long as t is greater than 1. So I'm replacing sine squared t by something that's bigger than it. So what I've got is that this is true, which is 3t. Now also, I'm getting rid of the denominator, see? I'm making the denominator smaller. So this thing is bigger than this thing. So what I just showed was that the integrand is less than or equal to 3 over t squared, which is what I wanted to do. Also, the integral from 1 to infinity of 3 over t squared converges. So by p equal 2, right? So by the convergent theorem, so does the integral. The trick is figuring out what to compare it to. Remember, don't worry about cosine y. That doesn't really affect much at all. This is basically behaving like 1 on top and y on the bottom. So I'm going to try to show 1 over y, that the integral, the improper integral, diverges. I'm going to try to make this greater than something over y, okay? Okay, here's how we do it. First of all, notice that for as long as y is greater than or equal to 1, isn't cosine y less than y? Less than or equal to y, doesn't make any difference. Right? Cosine of y is going to be less than or equal to y. So if you add 2y to both sides, I've got that cosine of y plus 2y is less than or equal to 3y. That's nice. So when you take the reciprocal, you get 1 over cosine y plus 2y is greater than 1 over 3y. I guess what I should have done is multiply by 3 on top. That's still true, right? So when you multiply by 3, it's still going to be true. Now I've got that 3 over cosine y plus 2y is greater than 1 over y, which is what I wanted. Now this integral diverges. Since this integral diverges of 1 over y, the improper integral from 1 to infinity of 1 over y dy diverges. So does the improper integral from 1 to infinity of 3 over cosine y plus 2y. That's kind of sneaky, isn't it? All right. Why don't you try this one? This one isn't too bad. Well, actually, this one is bad. This one's bad because the top is behaving basically like 1 over x. Okay, so 1 over x, the improper integral diverges. But the problem is, you see this plus 5 here? This integral is actually less than 2 over x. Even though I'm pretty sure this integral diverges, you can't just say it's, you can't just take away the 5 because that would actually make it less than a divergent integral, and that doesn't help you. See, so you got to be kind of sneaky here. This is how I would do it. This one's a little too subtle maybe, but look, if x is greater than 1, then isn't x plus 5? Look at the graph of x plus 5. Isn't it going to be less than the graph of y equals 6x? Just look at this linear functions. So I can replace x plus 5. X plus 5 is less than 6x as long as x is greater than or equal to 1. This graph is above this one. So when you take the reciprocals, this is true. 1 over x plus 5, since you take the reciprocal, is greater than 1 over 6x. Then if you multiply by 2 on both sides, it's still true. And I just showed that 2 over x plus 5 is greater than 1 over 3x, which is what I wanted. The integral from 1 to infinity of 1 over 3x diverges. And by the comparison theorem, so does the integral from 1 to infinity of 2 over x plus 5 dx. All right, here's the last one. This one, actually, the top is behaving like 2, the bottom is behaving like t, 2t, I should say. The top is behaving like 2t, the bottom is behaving like t, so this whole thing is behaving like 2. That isn't too hard to show, that this expression is going to be greater than or equal to 2. Look, for t greater than or equal to 5, this integrand, if you make the denominator smaller, this is greater than this, which equals 2, right? And it's not too hard to show that the integral from 5 to infinity, I just showed this in a direct way, the integral from 5 to infinity of 2 dt clearly diverges. That's easy to show. So by the comparison theorem, so does the integral from 5 to infinity of 2t over t minus 4 dt. All right, we'll see you next time. Bye-bye.